Now this is the problem of a vibrating beam, which is a fourth order PDE. It will get a little bit more tricky, but bear with me. We illustrate how higher order PDEs come about in the study of vibrating beam problems, and to solve the problem of a vibrating beam with simply supported ends by separation of variables. Our equation given here and boundary conditions here. This is known as the beam equation. The major difference between the transverse vibrations of a violin string and the transverse vibrations of a thin beam is that the beam offers resistance to bending. The resistance is responsible for changing the wave equation to the fourth order beam equation given here, where alpha squared equals k over rho. K equals the rigidity constant. For larger k, the more rigid the beam and the faster the vibrations. Then rho equals the linear density of the beam, which is mass over unit length. Now we consider the small vibration of a thin beam whose ends are simply fastened to two foundations. The ends are held stationary, but the slope at the end points can move. The beam is held by pins, let's say. Our boundary conditions here were given pictorially, where it's fastened on this end here, and the beam is free to vibrate or move up and down from one end. It is clear at the end of the beam should be u of 0 t equals 0 and u of 1 of t equals 0, but it's not obvious because our second derivative of x, u with respect to x is 0 t equals 0, and likewise for 1 of t equals 0 also holds. So using the theory of beams, we can show bending of the beam is represented by uxx, and a simply fastened beam can be described by the initial boundary value problem with alpha equals 1, which we're given here. Now if we use separation of variables and look for a solution of the form, again, u of xt, x of x, and now sines and cosines, where a and b are constants, and by choosing this we take the separation constant to be negative. We now substitute into the beam equation, which has a general solution given here. Now to find coefficients c, d, e, f, we substitute this expression into the boundary conditions, and we go through the motions again, and f equals 0, we get this, and our omega term n pi squared, and we get down to this part. It should be pretty straightforward to be able to follow this stuff. And now, since the PD and boundary conditions are linear and homogeneous, we conclude that the sum, instead of writing all this out again, I've just put this here. So we plug in this into here. Now, which is the sum of this. Now, this also satisfies the PDE and boundary conditions. Now we choose A of n and B of n in such a way that the initial conditions are satisfied. We substitute equation into initial conditions, it gives this here. So we're using the fact that sine n pi of x is orthogonal on the interval 0 to 1, which gives this, the orthogonality property. An example of a sample vibrating beam of u of x of 0 equals sine pi of x plus 0.5 sine 3 pi x, and u of t of x of 0 is 0. Now we could find a solution by substituting values of f of x and g of x into the equation in the box first given, but it looks simpler to look at the summations preceding it and observe that a of n equals 0, b1 equals 1, and so on, for all n equals 1, 2, and so on, so on. And hence the solution is given here. Now we note that the vibrating string solution given here, so the beam vibrates at higher frequencies than the string, which we already implied at the start. Now notes the beams are generally fastened in one of three ways. Free, meaning that they're unfastened, simply fastened, or rigidly fastened. Now another important vibrating beam is the cantilever beam problem. The solution to this beam is not the usual sum of products of sines and cosines, but is due to non-standard boundary conditions, which leads to more complicated solutions. And I'm giving kind of pictorially here to give an idea of this, and we'll get our solution here, which is our summation over n equals 1 to infinity. Now this is maybe the last one on this kind of problem in engineering mathematics. I'm going to do some general relativity next because I find that personally a little bit more fun, but please do like and subscribe because I've got lots more to come.